for the nice invitation to speak here. So, yes, I'll be supporting some joint work with Rupert Levine and Yvonne and Ludmilla, which in the audience. So I gave a version of this talk about 2 months ago. At the time, I said that the work should appear on the archive in about a week or two. This time, I'm going to make the same claim this time, and I'm much more confident that that will actually happen. So.
When is your next conference?
A month and a half, 6 weeks. All right, so maybe I'll report back in 6 weeks.
Post on this too.
Yeah. There's a legitimate probability that this will actually happen within 2 weeks. So, anyways, okay, stay tuned. Right. So I'm going to be. So there's a variety of examples of what we call quantum games, which are sort of examples of non-local games with quantum inputs and quantum outputs. We saw Carlos talk in detail about one particular class, the quantum XOR games. So I'm going to focus on the cooperative quantum games in the sense of Liang, Toner, and Watrous. And so here, a quantum game is specified by a pair. So so this is going to be a unit vector in this sort of question space, it's a Y, potentially with some auxiliary resource. So this is going to be your question, the quantum question. So this is going to be a state, let's say. And your predicate is going to be some contraction, some positive contraction inside, let's say CA tensor CB tensor HR. So it's going to be positive contraction inside here. So this is your sort of predicate. Okay, and here these are going to be sort of finite input output in the sense that sort of the questions and answers modulo this sort of auxiliary resource space are going to be finite. So here X, Y, A and B are just going to be always finite non-empty sets.
Does HR stand for referee?
Yeah, so this could be sort of the referee's sort of, or maybe some resource space. Yeah, so the referee would prepare this state. Potentially this could be sort of trivial, but they could also allow some sort of third party that the referee would continue to hold. Yeah. So here the strategies are now going to be given by quantum channels. From MX tensor MY into MA tensor MB, right? So this, of course, will just be the X by X matrices. And here, quantum channels, I view them in the sort of Schrodinger picture where they're really at the level of the trace class, so they're completely positive trace preserving. Okay, so one can picture these games. Right, the referee would prepare some tripartite state. I'm going to send sort of the first two legs, the first two systems to Alice and Bob. We're going to act. So Alice these are sort of Alice's questions in a sense, Alice's answers. Similarly for Bob's. So upon receiving this quantum question or state, they're going to act on their respective systems by their strategy gamma, which will then produce some output. And then the referee is going to measure with respect to P. It's a positive contraction, so it defines a binary measurement. Right? So you have some POVM, P1 minus P, which then you can assign two values however you'd like. Okay, and they're going to win if the measurement outcome is let's say 1 and then lose S. Okay, so that's one way to picture these games. And so for examples, of course, your sort of standard non-local game, 2-player single round non-local game would fit into this context in a natural way, right? So if you had your referee sending questions, classical questions to Alice and Bob, who respond with classical answers, then you could put this, and as I say, their questions are being sampled according to, you have some probability distribution, mu, on the question sets, and then you have some predicate function, let's say v, a, b, which encodes your winning conditions. Right, then you could, out of this, you can easily manufacture this sort of quantum. This quantum question would be just some purification of kind of the density matrix you would canonically associate with this set of questions, right? This sort of classical density matrix. You just put this on the diagonal, that gives you some density matrix, and you just purify this. So then this would be in Cx tensor Cy, and this would be your purification space, if you'd like. And then your predicate you can easily just put along the diagonal inside Ca tensor Cb, Cx tensor Cy. You just literally put it on the diagonal and you get your positive contraction here, kind of thing. Right, so of course the sort of classical non-local games fits into this picture, but also the quantum XOR games Carlos mentioned also fits into this picture, where there you had a list of states according to and some associated probabilities. So then you can just put that list, sort of purify them in the canonical way to get your question, and then using those coefficients Ci that the referee would use to judge whether or not they won, you could put them into, you could build sort of two POVMs, two PVMs, which you can then put together in a natural way to build your predicate P. So the quantum XOR games also fits into this model. Okay, and one way to think about, if you'd like, one class of examples, which I'll get back to near the end, is if P here were actually a state, so if you actually had a density operator, it would certainly be positive contraction, then really sort of the goal, Alice and Bob's goal, if they wanted to win this game, would be to actually convert locally. If they act locally on the first two pieces, they want to convert the rank 1 density associated to the question to rho. So really this is kind of like a state conversion game, if you'd like. You can think about it in terms of state convertibility. Okay, so I like thinking about them in the case when, for instance, if this is a rank 1 projection, then Carlos and Marius and Cooney and Perez Garcia, the whole paper studying this context of when this is rank 1, in which case you can interpret it as sort of a state convertibility game. Okay. So we're only going to focus on 4 classes of strategies. Okay, so the first 3 are sort of quantum analogs of the usual sort of classical correlation sets that one associates to just non-local games. So we're using this sort of Q, the C-loc, CQ, CQC, if you're familiar with that notation. But then we're also going to talk about just one way, LOCC, not 2-way. Okay, so what are these sets? So these sets, okay, they also, I mean, they're all dependent on X, Y, and AB, of course, but so this Q-loc, this is just going to be the convex hull of product channels. So you have, Alice has a channel, so does Bob. You take the local channel just by acting locally, but then you can also, you take some convex hull, which corresponds to having some shared randomness, let's say. Right, so another abbreviation for this class of strategies, which is often used in literature, is LOSR, which is local operations and shared randomness, which Carlos also mentioned in his talk. And in the Q sub Q, like this is really local operations, but then you allow some entanglement assistance. Okay, so one way to model that, so you have Hilbert spaces HA, HB, and you have a state, some density, let's say in S1 of HA into HB. So this would be your sort of entangled resource state if you'd like. And then you have channels. So B will go from MX tensor T of HA. So I guess I'm abusing notation. I'm using A here. So A, this just refers to sort of Alice's Hilbert space. So it need not have dimension cardinality of A, but in any case. So Alice and Bob have channels of this form. So this is, I wrote T, didn't I? Yeah. See, that's what happens. So that's one. And then here you have S1 of HB into MB. And then the resulting, what is the strategy? The strategy is, I mean, effectively it's just the tensor product. So gamma takes rho into, okay, I'll write phi tensor C of rho tensor sigma up to a flip, right? So there's going to be some flip here. Just so you can actually make sense, but that's more or less what it is. Okay, so you're acting locally, but you allow some sort of entanglement assistance here. So CQ is really entanglement assisted local operations. Right. Okay, then you have the corresponding class for CQC. So here it's very analogous to the sort of usual non-local game setup where you have a single Hilbert space. H, and you have a state in S1. Okay, and then you have these channels . A, similar for Bob. Okay, but now these channels, they have to commute in some sense, and in what sense is that? So such that sort of if you look at their adjoints, I'll just say the adjoints have commuting entries in B of H. So if you take the adjoint of phi, you're going to get a UCP map now from matrices into matrices with entries in B of H. Similarly for Bob's channel, right? And so you want those entries, sort of the operator entries. So it's determined by basically a family of matrices whose entries are in B of H, and you want those entries in B of H to commute, right? And so that's going to happen here if you think of this as sort of the global. If the global Hilbert space is actually factors into a tensor product, then you take these adjoints, then their operator entries, in this case, Alice's will be supported solely here. They're acting trivially on Bob's and vice versa, right? And so they're going to trivially commute.
And entries really means the matrix entries of the dual map.
Yes.
Which are just matrices in B of H, and there they can commute.
Yeah. Right, and so because they commute, then this allows you to write, you can view this map. So now I'm taking the adjoints here. So now I'm going to view this map as a map from M, A, B, A tensor B into mx tensor my tensor b of h, where here I'm taking multiplication, but just in the right place, right? It's defined sort of in the only way that you would write it down. Okay, but this is well defined. It actually as a linear map using commutativity of these entries. Okay, then you can write your gamma. So then the resulting gamma from mx tensor my, it's going to be the pre-dual of this thing. Evaluated there. Sorry, and I guess I'm forgetting a row here. Yeah. Row maps there. I think that's what I want. Maybe I'll use row, it doesn't matter. The map doesn't flip. It should be row. That's your segment. So it's very much, I mean, it's really just sort of the commuting operator analog of this, if you'd like. Right. Okay. So those are the sort of the three, and maybe before I mention the fourth, so there's a canonical. So if C loc is your usual correlation set, the set of bipartite conditional probability distributions that you generate using convex combinations of product distributions. These are the usual sort of classical correlation sets, right? Then any classical correlation bipartite generates a quantum channel in the canonical way, right? And this association gives you inclusions of these sets here, right? So this usual sort of hierarchy that one studies in non-local games, it sort of sits inside this one in a natural way. And you can actually go back, I mean, and it's all very canonical. You can just, if you start with the channel here, you restrict the diagonal. Who cares what it does afterwards, because you can always just project back down to the diagonal, and such a thing would give you a classical channel, right? So basically, if you look at just the classical channel versions of this, you recover the usual hierarchy in terms of conditional probability distributions. And then the last one will be this one-way LOCC. Okay, so this would be a slightly different formulation than, well, Carlos was in he was in a sort of a semi-classical, he had sort of quantum questions, classical outputs, but he talked about LOCC, but here I'll just sort of write out sort of the one-way definition in this context. So this guy is sort of one-way LOCC if there exists CP maps, some family of CP maps on Alice's side, and channels, let's say, sorry, CP maps so that the sum over I is a channel, and channels on Bob's side, such that gamma decomposes in this fashion. Right, and so how one typically interprets this is, I mean, if you think of a measurement, if Alice has a measurement system, and this is sort of parameterized by this finite index set, she would perform that measurement, send the result, the classical outcome to Bob, and then conditional on that classical outcome, he would apply that corresponding channel, right? So that's the typical way one thinks about this class of channels operationally. Yeah, but now, more generally, you can allow yourself an instrument in this fashion, which I came up in a previous talk. Again, parameterized by some classical output, but it's shared between Alice and Bob. And then he acts accordingly. Okay, so given a quantum game specified by C and P, we want to examine the probability of successes by playing this game using a variety of resources. For us, just these four in this talk. Okay, so if T is one of our parameters, then we let the T value is the probability of success, the maximum probability of success, given that you play with such strategies. So if you take the sup over gamma in this set, and here we're going to take the overlap of the image of the question with the predicate. And so this is the probability of success of, if you played the game with this particular strategy, then this would be the probability of success with that strategy. So you just sup over all that. Okay. Right, so in this context of rank 1 quantum games, which I mentioned, so this was Cooney and Carlos and Arias and Perez Garcia, so they analyzed a variety of values and one result in particular. So here you have some unit vector in the answer space. Look at the corresponding rank 1 projection. And so there they computed the value, so the QT value, the Q value of any rank 1 game. They showed that this is given by a certain tensor norm. So if you take the partial trace of this rank 1 operator, they showed that this is given by the min norm in the square in the trace class. So here, this S1B, this is the trace class. So one of the many results in the paper, they investigated this. They also computed the value under one-way quantum communication and related that to the Hagerup norm. Okay, but this result was one of our motivations. So given this, it's sort of natural, and given these other sort of this canonical hierarchy here, right, it's natural to want to see if we can extend this with the other classes. So here, maybe just as a remark, so we're viewing, I mean, you can view this, at the end of the day, this is just going to be some finite dimensional tensor, right? So you can sort of put it in any space you'd like, in a sense, and put any norm you want on it, but you can also see it canonically sort of as a map from CA tensor CB into CX tensor CY. Right? So then as a tensor products of individual mappings, and here you're taking now the min norm, so this is the operator space, the minimal operator space norm, as in Carlos' talk, of the trace class here on either side. Right, so you can view this as, this is a particular tensor which you can associate to a quantum game. Right? There's not just one way to do that, but this is one particular tensor that you can associate to it. Okay, and so a result, I'm going to write the theorem in a way that I always tell my students not to.
Can I object a little bit?
Please.
I think this is from me. It's AX to BY, right? I mean, from matrix algebras to Schattenclass, if you do the min value, I mean, you of course, I mean, you can flip-flop all these tensors around, which makes it difficult.
Yes.
But then it's from matrix values to Schattenclass. That's what Carlos had this morning, right? So if you do
Yeah. So it would
matrix
be,
algebra in AX to Schatten operators in BY, you get exactly the CB norm of the corresponding map.
that's right.
Yeah, and that's the min value. That's the connection to Carlos's talk this morning.
Yeah, exactly. So you could
You
also
get the epsilon value, but you know.
exactly. So you could see this. This is CB from B of CX CA into S1 of CB. Yeah.
Because this gymnastics is something you have to learn.
Yes.
You know, to deal with these kind of things.
Right. So this is yeah. I mean, so you always have yeah. So you have V star tensor. This guy always sits canonically as a map between W, right? Just by slicing with the suitable.
It's just
function.
gymnastics.
Yeah. Yeah. So if you prefer to think of it as a map, which is I mean easier to imagine. I mean, depending on your taste, then yes, that's exactly this. Yeah. Yeah, and in what's to come, I'm going to we'll sort of always sort of in the tensor norms I'll describe, we're often going to use this. Yeah. Right. Okay. So let's let G be this quantum game here, and now I'm going to assume that P. So I'm going to say that P has a discrete spectrum. So we're going to look at some discrete. It's a spectral decom, so it has discrete spectrum. I'll just take a spectral decomposition of P. Okay, and I'm going to just let rho associated to the game. I'm going to let maybe rho G for the game. This is going to be, I'm going to put basically take these mappings for each I, and then just take sort of a column of them. So I'm going to take the square root of lambda I, trace C A to I star, and I'm going to view this as some potentially infinite column. So M infinity 1 of, okay, just algebraic. I mean, okay, I'm gonna specify which norms we're talking about here in each individual context, but I just want to sort of set up some notation. Okay, so I'm going to view this as an infinite column. Right. Okay, so first thing, so there's not really much more to say. I mean, in the quantum case, you just get exactly this, but the column version, so that's fine. Right, so then, yeah, so maybe I'll just list it. So then, the quantum value of the game is exactly just the column structure of, so you have M infinity 1 of this min space. So nothing really new. Proof is the same. Okay, so what about the local value? So this is going to be, so it turns out to be a tensor norm which appears in more recent work of Marios and Carlos and other collaborators, Kubicki and Perez Garcia. So this is going to be the CB weak Hilbert-Schmidt norm. S2, I think WCB. There's a square. Can't forget the square. Did I forget it? No. Okay. All right. So what is this beast? So, okay. So, yeah. So I'm going to have this theorem, and I'm going to explain each property within. So. I have a terrible presentation, but anyways. So what is this? So how does one define this? So if you have operator spaces, then you have a family n by n matrix of linear maps between V and W. and then you can put them all together in a canonical fashion to view it as a linear map here. And how does one define this norm? So here, I'm going to automatically appeal to this kind of inclusion here, and I'm going to define the norm in terms of this way. Well, define it as they did. Okay, so for such a norm, so this S2, just sort of weak CB norm here is defined as follows. So you take the soup of beta to the n composed with phi, composed with alpha. This is going to be a map. So alpha is going to be a complete contraction from this row space. So here I should have used R. So maybe I should say L2 with the row operator space structure into V. And now beta is going to be a mapping from W into the column structure here. These are going to be completely contractive. And you're going to view this guy as a map from L2 of R into Mn here.
So, Jason, in the notation above, so AB are By, I guess, but what are the letters under the tensor product? What is it?
This was, I think so this was WCB S2.
S2, okay.
Yeah, so the connection with S2 will come,
Okay.
if it's not already sort of there, it'll come in a minute. So we take the soup over this value, and so at level 1, then what's going on here, so you can sort of picture it in terms of these diagrams. So what you're doing, so it's not quite a sort of traditional factorization of your map. But what you want to do is you want to take complete contractions. So you take mappings from L2 into V and from W into L2. But you want these to be completely contractive, first with respect to the R, the second with respect to the column. And then you take the CB, this turns out to be the Hilbert-Schmidt norm. So you take the Hilbert-Schmidt norm really of these compositions. So if you take CB, what this is it's really the Hilbert-Schmidt, or S2. Isometrically, this is true, right? So really you're taking, so this CB norm really, at level 1 here, this corresponds to just really taking the Hilbert-Schmidt norm of these compositions. So this is this kind of CB weak Hilbert-Schmidt property. And I mean, I assume, so maybe Marius and Carlos can correct me, but I assume this sort of weak terminology comes from the fact that this is not quite an operator ideal, but sort of a weak operator ideal in some sense. I mean, it satisfies the compositional property for mapping ideals, if you'd like, but it's always, this norm is less than or equal to the CB norm, so it's not quite a mapping ideal in the usual sense, but
Yeah, kind of in between two categories.
right, yeah,
I mean, another way to think about it is you take this S1AX and send it to the column. You send S1BY to a column, and then you calculate the large column of everything, because that's another column.
exactly. Yeah.
And then you can, we had some crazy definitions in the ancient times of what is the column structure of an operator space, right? And
Right.
that fits into that context. That's an internal way to describe it. So
Right. Yeah, and so it's quite believable. So if you think, so in a sense, what are these? I mean, if you have a completely contractive map here, then this is really governed by some column. In a sense, I mean, like, how do you produce complete contractions here? Really, you're talking about columns with entries in V, which are contractions, so column contractions, and these are precisely, in a sense, given your Krauss operators for either Alice or Bob's channel kind of thing. So this supremum given by the value, really by convexity, you're just restricting to product channels, and then these more or less where these come from are just really your Krauss operators for the channels. Sort of one direction. Okay, so the next one, I'm going to go to the one-way LOCC result here. So Carlos mentioned that for quantum XOR games, they've shown that the one-way LOCC bias for these quantum XOR games is equivalent to a sort of pi1 CB summing type property. And so here, so that result motivated in part would become here. So just put a pre, so we're going to let pi2c, this is going to be of a map. So let's say, let's let V, these guys be operator spaces. This will be 3. And we're going to let, so phi is going to be some linear map, and you want to look at this pi2c or pi2cb norm of phi, and what you do is you amplify and you let act. So here Carlos was talking about pi1 min, and then you had just L1 of trace class here, right? And so one can do this. So Marius introduced these properties, this kind of partial, extension of the usual sort of classical notion of two-summing or p-summing maps in Banach space theory, right? So if this was the injective Banach space injective norm, right? Then this is this usual two-summing property, right? And a mapping's two-summing if it takes any weakly square summable sequence to a phone norm, strong square summable sequence, right? So this now if you put an operator space structure here, then you can make sense of the min, and then you can also talk about here. And so there, one can use the interpolation structures here, but we want to use the column structure. Okay, so you say that this guy is 2C summing if this quantity is finite. Okay, now, but what we needed is so this is just, in this definition, you're using the operator space structure of V here, but just the Banach space structure of W. But what we needed a sort of, what is the sort of operator space structure on L2 of W relevant for our purposes? And so it turns out that it's the following. So the following matricial norms, so if you take, so if we have a matrix of sequences, so K is going to be your sort of sequential index, the IJs are going to be the matricial index, so this MN of, I knew I should have, well, whatever, let's go to the next line. Okay, so you have, maybe I should have done W. So if an n by n matrix of sequences, so K would be your sequential index, so we're going to find this to be the soup of norms of phi k x I j k. This is the sequence, the matrix, and now here this is going to be mn of L2 tensor H C. Okay, where each phi k is going to be some complete contraction into some Hilbert space with a column structure. Okay, so it's some kind of column quantization, if you'd like, of L2 of W, but what's important here is actually, so maybe I should finish the statement. So the matricial norms define an operator, it's an operator space structure, but actually it's more than that. There's a canonical module structure associated to it as well. Right, so L infinity, just diagonal matrices here, right? This is a natural Banach module over L infinity. You just act on this component here, right? You act component-wise. Okay, and with this, you could tell, this family of phi k's, families into Hilbert spaces, this is really parameterized by some k. Really, these are going to be these. What are the L infinity module maps from this space into something? They're going to be of that form. Okay, so this is defined to make this sort of a canonical operator L infinity module. Yeah, that's sort of where it comes from. Okay, and this L infinity module is really what corresponds to the classical communication in our result. right, and so how do we define this? Okay, so you have, let's say you have, so given phi, which is a matrix of mappings here, and you want, we're going to want each phi ij to be 2C summing. So we can define this. Okay, then we put this sort of nth amplification here to be the sup. So it's defined in a similar way to the weak Hilbert-Schmidt property here, but we're sort of incorporating this two-summing structure as well. So it's going to be the sup of betas in tensor phi composed with alpha. Where is this map now? So this is a map from L2R into Mn of L2C. CB norm of this, okay, where alpha and beta, this guy goes into the min, and beta goes from this base L2 of W back to the columns, and these are going to be completely contractive, but now L infinity module maps. Here, where this module structure is going to be always with respect to the left tensor leg in all cases.
And that makes it classical.
Exactly. So that allows you to sort of, in a sense, synchronize these mappings, which corresponds to the classical communication. Yeah. So at level 1, you have this. At level 1, we have this kind of, in a similar spirit to this weak Hilbert-Schmidt property. Now we have L2 tensor min, and now you have id tensor phi of L2 of this guy, and you want beta, and beta is completely contractive with respect to this structure here. Okay, and so here you're sort of taking the Hilbert-Schmidt norms. So at level 1, this, by the same kind of argument, this sort of reduces to kind of a Hilbert-Schmidt norm. So you're taking, again, this is some kind of sort of weak Hilbert-Schmidt in some sense, but there's some additional overheads here. But yeah, so the point is that the L infinity module structure really captures the classical communication, because if you want such a map here to be a module map, right, then it's going to have to coincide. I mean, it's going to have to map the ith basis vector. It's going to have to keep that subspace invariant, right, by the module property. So maybe I'll say VI, right? And so you're going to necessarily have this structure. And so there's your classical register, which records the classical communication. And then here you're just you're leaving that invariant, and the betas are also leaving that invariant. And actually, what is a map from here to here? It's going to be, if it's a module map, it's going to necessarily come from a tuple, right? And then this tuple is going to have to coincide, because this doesn't spoil the module property. The tuple will automatically read off this, and there's your sort of synchronicity in a sense. Right. So the one way, this is very disorganized, but anyways, so the one way LOCC value of the game is going to be this particular norm. It's going to be the sort of infinity 1 amplification of this operator space structure on this column row with the square. And so, and when n is equal to 1, so we don't have, well, we need this column structure. So in particular for rank 1, for rank 1 games, we actually just recover the two column summing norm of this map. Well, the trace, I guess there's still the trace around. Yeah. So similar to, so in Carlos's, or recall in his talk he mentioned that in the case of quantum XOR games, the one-way LOCC bias was equivalent to sort of pi 1 there. But there, sort of the game tensor is different, right? There's not a unique way to associate a game tensor. This is like some kind of purified version or some L2 version in a sense, right? And I'm always forgetting squares here. Right, but as a corollary of this, we obtain a tensor norm characterization of LOCC convertibility, at least for pure states, and not just one way. Right, because we can rely on a nice result of Low and Popescu. So if C and eta belong to the same space now, so A is X, E is Y, then you can convert C to eta using not only just one-way LOCC, but any LOCC, because we have two fixed pure states. This is equivalent to this C summing norm of this guy to be 1. Yeah. Because if you can convert, so for two fixed pure states, if you can go LOCC, then it turns out you can always do it using a one-way LOCC. And if you can convert perfectly, this is certainly 1. And if you're 1, you can do it approximately, but then if you can do it approximately for every epsilon, you can use the majorization technique combined with Nielsen's theorem to get back the other way. Right. So about 5 minutes, 10 minutes, is it 5?
Well, with questions, 10 minutes.
Right, okay. Yeah, so this was, the last piece was that, so this QC value. So what is the QC value for these quantum games? Okay, and so this is going to be the norm squared of rho of this column. And now this is going to be, I'm going to say the T max norm. So what is this? So this is perhaps not surprising. So this is going to be the maximal TRO tensor product. Okay, so this was defined by Core and Ruan. All right, so if you're familiar with T, so TRO stands for ternary ring of operators. In one sense, there's some kind of like rectangular C-star algebras if you haven't seen them before. So B of HK for different sizes is a TRO, right? You take RST goes to R S star T, then this is a well-defined composition, right? So in a sense, so you can you can't multiply two rectangular matrices together unless the dimensions coincide, but they always have this ternary structure. Also, it's known that TROs are always corners of C-star algebras. You have these sort of linking algebras, and they're these sort of left and right C-star algebras. And this becomes a bimodule over these sort of left and right things. So they're very closely related to C-star algebras, and this T-max norm was defined in the exact same way that it's defined for C-star algebras. You just take TRO morphisms into the same Hilbert space with commuting ranges. Okay, now, 2 remarks. So what allows us, we have trace class here, so why can we write this? So S1 AX, so this sits canonically into this universal TRO of a block operator isometry defined by Von and Zumilla. So this is sort of the universal TRO for the relations, so generated by VAX, so that if you sum over A, you want this to be an isometry. If you put all these things together into a rectangular matrix, you want this to be an isometry. So if you want to encode, you can encode those relations as follows. So if you had VA prime X double prime, this would be delta X X prime VA. And there should be, there we go. Right, so it's sort of the universal TRO satisfying these relations. So representations of this thing are always going to be block operator isometries, in a sense. Okay, and so it turns out that this, not surprisingly, the trace class actually sits. If we take the matrix unit, probably with X and A, this turns out to be a complete isometry, which isn't surprising. It's known that if these are square, if A is equal to X, then this trace class space is isomorphic as an operator space to the order 1 subspace in the Brown algebra, the universal C-star algebra generated by a unitary. Right, and this operator space is also, trace class is really, what are the complete contractions from trace class into operator spaces? They're matricial contractions. Right, and so if you're matricially contractive, right, you can either be matricially contractive or you sort of a matricial isometry or a matricial unitary to get these dilation results. So it's not sort of surprising that this is also complete isometries. So we're viewing this inside here, and this allows us to make sense of this quantity. Okay, but the bulk of the proof is actually a reformulation of the way that this tensor product is defined. So it's defined in terms of commuting TRO representations, but that was somehow too strong for us. But we have this. So at first we thought, okay, maybe this is sort of a different tensor product. Turns out they're the same, but we've defined a different. Well, we've given a reformulation of this tensor product, not in terms of commuting TRO morphisms on the same space, but somehow semi-commutation. So you want somehow, well, yeah, I have a minute. So in a sense you want, so if you have TROs, let's say, so you want a mapping from V into BHK, and you want to, so you have a mapping, let's say psi from V into there, and you have a mapping phi from U. These are sort of TRO representations, KL. Then how do you define this norm? I'll just do it on simple tensors so you get the idea. So this is going to be, you take the sup over phi of U times the norms here, these operator norms here, where you don't demand, so these are in different spaces, they have one common component here. You want sort of the sort of right version of this guy, which is a representation of the right C-star algebra of V, to somehow commute with the left version of U, right? So any TRO morphism, you have this sort of left and right C-star algebras associated to this, and a TRO morphism is always going to induce star homomorphisms from the left and the right algebras. And so what you need is you need that the left algebra associated to this representation commutes with the right algebra, and not that the images of these morphisms actually commute. So it's easy to construct examples where this sort of semi-commutation property is strictly weaker, but taking the supremum doesn't matter. So the bulk of this proof actually is sort of a reformulation of this tensor norm. Anyways. Okay. I think my time's up. Thanks.
Thank you very much. Questions?
So I think there's a little help for this TRO business if you write Schatten AX as rho A tensor Hagrow column X. And then there's a theorem by PZ that the Hagrow tensor product, SAX, not the max, just one component. This is rho A.
Yes, that's right.
Tensor Hagrow.
Yeah.
CX.
Sorry, yes, of course.
Yeah. So he has a theorem that the Hagrow tensor product always embeds into the free product, because rho A embeds into a matrix algebra, CX embeds into a matrix algebra. If you embed it there in these universal objects, then you're getting the right answer.
Yeah.
But of course you're paying this universality price, which you're paying exactly the same, and they're not symmetric. So this is your TRO structure, right, and column. So that's kind of a nice technical way. And then I also have to say, I know that this stuff is hard because of the notation, so you survived.
Thank Yeah, thank you. We do use that fact actually. The Hagerup embeds.
Yeah, that's kind of, these are the tools you can use, right?
Further questions?
Just one brief question. So, if you follow the approach that you have followed in order to describe the one-way classical communication, to do the same for the quantum communication that we consider,
Right.
is it clear that you could end up with the Hagerup tensor norm, or it's not clear at all? Because at some point we proved that if you use one-way quantum, you have to consider the Hagerup tensor norm.
Yeah.
But I don't see, well, I mean, at least not here.
So yeah, I was wondering. I thought a little bit about this, trying to put this result in that context. So you can phrase the Hagerup in terms of. Where is it now? Gone, perhaps. Yeah, you can phrase the Hagerup right in terms of like mapping from this space into column projective W, right? So there's a this reformulation of if you have like of gamma 2, right? Yeah, because you have, so if you have gamma 2 from W into V star, something like this, or maybe gamma, this Hilbert space factorization, which you can relate via duality to the Hagerup tensor product, you can express this in terms of mappings like this, but into column projective W. And so I was trying to sort of try and put that perspective of the Hagerup tensor product together with this to sort of see how they would fit together, but it wasn't clear. There was some row and column issue already, but yeah, I think that'd be very interesting to try and
Yeah, at least to try to unify
yeah,
the two approaches.
And then do it for 3.
3. Yes.
I mean, it sounds like we're just doing tensor nonsense, but for 3 we just really don't know. And
Yeah, of course. Yeah, everything is defined in terms of the
then
mappings. Yeah.
think of your conversion theorem, right? I mean, if we were to do this for 3 tensors, we would be very lucky.
Yes.
Just saying.